All right, so let's talk a bit about the stepping action class. So I'm already in the good old build directory of our simulation project. So I'll just quickly visualize the simulation geometry to set the context. So remember that currently we've got a air world, which is meter cubed, and then inside we've got a smaller water cube shown visualized as red in this case. So hopefully you remember when I was talking about the hierarchy of runs, events, tracks, and steps inside Geant4. Oh wait, I wanted the run electron. So let's just quickly do a quick refresher of that. So let's now shoot a electron with 1 MeV and have it starting at minus 50 centimeters and go in the plus x direction. In the plus x direction. So just make sure I've got it compiled. Yep, all good. So let's just run the simulation with the run electron Mac. So hopefully you remember from before with when we, I should just point out, so I've got the tracking verbose set to 1. So when we run the simulation, we get all this track information spitted out. So remember that when we have the tracking verbose, we can see each event. So remember the Geant4 simulation, the run. So when our first particle gets shot to the very last particle which is shot, this run, it's made up of multiple events, and one event is when we shoot one primary particle. In this case, it's an electron with energy 1 MeV, and each event is made up of multiple tracks, and one track represents the history of one particle's journey. So it's from when it is created to when it either is absorbed, loses all its energy, or leaves the world volume, or if we artificially kill it. So in this case, we've shot an electron, so it's got a step ID of 0 of when it's created, and we get all these informations listed about it, and we see every time there's an interaction or a physical process occurring, we get another step occurring. So for our first step, so step ID set to 1, there we saw that multiple scattering occurred for the electron, and after this an ionization event occurred, and we can see the energy lost by the electron and so on. And remember, whenever there's a volume change, then that will also force the track to have a step. So in this case, the particle or the track goes from the physical world, so the air world, into the fizz box, which is the water cube, our water cube in the center of the world. And we see the position where this occurs, and we've got all this summary of all these steps. So it'd be very helpful if we could access all this information in the simulation itself, like not having to set the verbosity to 1, as in the tracking verbosity in the macro. But it'd be nice, for instance, if we wanted to look at the energy deposited within some volume. It'd be quite helpful if we could just, store all the energy deposited in some volume. So one way to do this is with the stepping action class. So just want to go in your source directory and open stepping action .cc. So what this class does pretty much is it gives you access to every step in the simulation, and allows you to access some allows you to access all the information which is contained in the step. So if you just Google G4 Step class, then you can go to one of the links and you'll see all the member functions that you can run with the G4 Step class. So these are more or less all the information you can retrieve when you use the stepping action class. So if you go through these, you can view various information, but I'll just go to our stepping action class now. So I've already got some helpful functions already included. So in our first case, we've got step number, and we've got parent ID and EDEP S, pre-K, or sorry, I'm just reading out the variables. So step number, as you'd expect, it gets the step number, and all these other names. We've got position, so post X gets the position of a step, and we've got Kanane Kanji, and we've got pre and post. So in your stepping action class, when you open it, you'll already see some information already given as examples. So let's say if I just want to spit out the step number. So let's go step number equals step no, and let's say parent ID. Oh wait, left off the text there. So parent ID equals parent ID, and let's just end that line there. And let's also just add the position of the step. So let's go post X equals, whoops, what was the variable called? So post X. So I'm just outputting all these variables I've got. And let's have post Y. So post Y equals post Y. And I'm also just quickly gonna add, oh, there's already pre, but I'm also going to add a pre-Y, and hope you should be able to see why I'm doing this in a moment after I run it. So let's just copy this line and paste it. So let's just change this to pre, and then change this to pre. Oops, change this to pre, and this to pre here. Pre-Y and pre-Y here, and let's just compile that. So let's just run that simulation again with the electron macro. So it's assuming that 1 MeV electron from the same position again. So if we scroll up to the first track, so when the parent particle, sorry, the primary particle is generated. So here at the step ID equal to 0, where the particle is created, and then the step ID set to 1, where the first interaction occurs, so multiple scattering. We see our stepping action class spitting out its information, so all this stuff here. So our first line was step number equals 1, parent ID equals 0, post X, position, all that good stuff. So one thing you might be thinking, why we don't have a step number equals 0 being printed to the screen. So when the particle is created, it hasn't really got it's so the stepping action, like when we're looking at steps, a step is a snapshot of the track. So when it's created, it hasn't undergone any changes, and that's sort of what the stepping action is looking at. So we can never access a step ID of 0. So when it's created, for that we have to do something else. But so we're accessing the first interaction of the step, like when we actually access the tracks step. So let's just go to the next line where we've got the position. So we've got our position printed out here, so much more higher precision or information, just because the tracking verbose will just print it out for a certain decimal point, depending on what it feels best. But you see we've got this post and this pre X and Y. So this is kind of one way where we can access the step ID of 0. So when we're with our step, we've got a pre-step and a post-step, and the pre-step is just where the particle was in the time before the current step. So when this is being called let's go to stepping action. So when this code is being called, or when it's accessing the step, when it says access the post step, what it's saying is pretty much access the current location when you're telling the stepping action to give it the post. Whereas when you're giving it the pre, it's saying where was this particle before this current step. So if you like, you could kind of think of as the post step as the current step, and the pre as the previous step, which is pretty intuitive with the name. So when we actually print out the pre-X for step ID equal to 1, we're actually getting the position where the particle was generated. So in this case, we've got 500 in the X and 0 in the Y, so which lines up with our step ID of 0. And you can see this for all the other steps. And if we go to the end of the track, if we just go down and search for it, so a final step here at step ID I28, you see here it looks like the electron lost all its energy, with ionization being the final process which killed it. So here we've got the final position information here, and then once we've got this electron here, which was created from one of the ionization processes probably, so it would be the most high energy electron, since our production cut for secondary particles is still pretty high. So if we quickly look at the change, where's the highest? I won't bother looking. But anyway, so this is just one of the ionizations, and again, you see all this information. So the stepping action is just pretty much giving you all the access to what a particle is doing at any one point in time or in position. So it's very helpful if you want to score certain quantities, such as like if you wanted to count the fluence or record the fluence, of particles for a certain position, or if you wanted to get the energy deposited, as I said earlier, or if you wanted to see what type of particles were at certain positions. So one other thing I'll also point out here is you can also access the volume which the particle is currently in. So I'm just going to slightly change this now and print out the particle name here. So, oh, sorry, that's the actual, I don't want particle name. Sorry, I want the volume name. So I'll print out the pre and the post again. So I'll just go prevol equals, oops, prevol equals prevol, and post vol equals post vol. Oh, what have I called it? Oh, post vol. Just put that there, and so let's just run that 1 MeV electron again. Look at the output, and so if we go to the volume names, here you see for step ID equals 1, it's pre-volume equals physical world, post-volume physical world, and let's just go to where it enters the physical box. So step ID 5, the particles entering the physical box or the water cube in the center of the world. So if we go down to the printout for the volume names, we can see the post volume is the phys box here, and the pre is the physical world. And whilst we're at this boundary condition, I just wanted to reiterate one point that I made in an earlier video, is if we look at the coordinate or the position of the track / or the step, we can see when it enters the physical box or the water cubed, that the coordinate system doesn't change. It's always with the global coordinate system. So one thing to be careful of is, say, if you're trying to get the depth dose in a phantom or a water cube, then when you're scoring that position, if you're using the stepping action to get its position, then you'll have to take into account where in the world that the phantom is located, since the stepping action or all the tracking information is always in terms of the global world coordinate system. So if you actually want to, adjust for the, like if you want to make the water phantom starting at 0 millimeters instead of the global coordinate system, then you'd have to add some shift to the output. So let's say in our case, our phantom is a 250, as in the range of the phantom is minus 250 to 250. So in that case, we might plus an additional 250 onto our X position. So we might go something like plus 250 millimeters if we wanted to shift the coordinate system. But just be on the lookout for, like, when you're getting the position information of a step, that it's always going to be the global and it's not local to the volume that it's scoring in at that moment. And while we're talking about volumes, I'll just point out this top if statement here, where we check the step, where the step is the current snapshot of the track, that it checks whether the step, whether it's in a volume that exists. So all this is saying a step, get track, get next volume. So if the next volume exists, So, you know, if this is fizzbox or physical world or something like that, if that's what the next volume returns, that means the track is still alive for that step. But let's say, for instance, that we called the stepping action after this track had died, then it would be trying to access something that doesn't exist, and then we just get an error. Well, would get a segmentation fault if you try to run it without this. In fact, if I could just get rid of this if statement, it might actually do that now. So if I just quickly compile, then okay, in that case, none of the post volumes were non-existent, so it didn't care for that case. But for some other quantity, it's much more sensitive, so it's always important to have this if statement here just to make sure that the information actually exists. Otherwise, it'll be trying to access information that's just non-existent, so it'll just give you garbage results, if any. So this was just a bit of a introduction of what the stepping action does. So all it's doing is giving you a snapshot of what the particle's doing. So from that, you know, we can store quantities. And in the next video, I'll show how you can actually store some quantities with the stepping action.